Okay, so now I'm going to show how to reason about connectives and quantifiers. You know, these are always extremely important. And we saw in the previous lecture how to reason in a backward fashion. Now we have the tools to reason forward. Now, the good news is that everything that's part of this segment is it's going to be things that you already know in some sense, right? Because you know how to reason forward, and you know how to reason about connectives and quantifiers, and it's just going to be a combination, a very natural combination of the two. However, it's so important that it's worthwhile to do some exercises in that style, and also to watch me do some exercises in that style. So that's exactly what I'm going to do now. And I should really open that info view window and put it at the right place. That's going to come in handy, I guess. The first example is commutativity of conjunction. And so now, okay, well, the proof is already given. There's not much to learn from such a proof. It's better to start from scratch, right? And I hope nothing bad will happen, because you know, no 5 plus 5 equals 25 like yesterday, but we'll see. You know, I'm human. So I'll try to write that proof and see if I'm not too rusty since last year. Right. So what's the first thing I do here? Well, it's almost always the same. You look at the topmost symbol. You're like, what is the topmost symbol of that expression? And it's definitely not the conjunctions. It's the implication. And then you're like, how can I, you know, what do I do about an implication? What do mathematicians do when they want to prove that A implies B or foo implies bar? Well, they assume foo and then they show bar, right? This is exactly what we're going to do. Assume, let's copy paste this. We need to give it a name, so we're going to call it HAB. I think that's going to be a good name. Comma, don't forget the comma. And yeah, Lean is quite unforgiving for these little syntactic mistakes, so always be very careful. Otherwise, you get very strange errors, and even I then just cannot make sense of them. Okay, and then I write the show. I hurry up because I don't have a complete proof now, so I want to show then the A comma from, and then I need. I can write sorry, you know, that's not a bad choice, but I can do better. I can put an underscore here. So now Lean complains there's an error, but at least it doesn't complain about the syntax of the whole proof. It only complains about this hole here. You see there's no other red on the screen. And then it says, oh, it doesn't know how to automatically provide a proof of the right, you know, of B and A in such a context. Okay, no wonder. But you see, it gives us some information, and this is how we're going to develop proofs. And this is how you really should develop proofs, structured proofs in Lean, by putting underscores whenever you don't know what goes there. And that should remind you of the procedure we use to build terms, right? So building structured proofs and building, you know, inhabitants in lecture 1 is, you know, basically the same game. And that's why I was saying, you know, wax in, wax out, and so on. You know, what we were doing back then is useful now as well. Okay. So now what do we do? Well, typically at that point, the trick is to put some intermediate steps. So to think in the forward fashions, like what are we trying to do here, where we're trying to go. So do a bit of planning, if you like, not just let Lean tell us where we want to go. So in this case, okay, we have A and B. Well, a mathematician might say, of course, mathematicians would never engage in such levels of details, but if they would, then this is what they would say. They would say, well, if we have A and B, that means we have A, and that means we have B. So we're going to extract this information. We're going to say have, have HA. HA is just the name I give it, right? And then, well, I'll give the proof later. We're going to have HB, yeah, do the proof later. And now we have three holes in our proof, but we see where this is going. So, you know, once we have A and B in our hands, we can form B and A. using the introduction rule of AND. So we're going to say AND intro B, HB and HA, right? We have to call the properties by their names, not by the property itself. And that's it. That closed one of the holes. You see, this is what I meant. This is something we already knew from before. The introduction rule from AND takes, you know, a proof of the left-hand side, a proof of the right-hand side, and it yields a proof of the whole thing. Right? This is what we see here at the bottom. M1, M2, M1, M2. All right, so you have to provide them in the right order. That's it, B before A. Right? If I put A before B, wouldn't work. Okay, and we're lucky the proof still compiles. And now we need to extract the A from AB. So that's going to be an elim. And you remember there were two elim rules, elimination rules for AND. There's the left one and the right one. We want to retrieve A. A is on the left-hand side, so we're going to do a left elim, right? So AND elim left of HAB will give us the A. And I think you know what's coming here. And that's it. And the whole rest of this session here is of the same style. So we have an OR swap here, right, which is a bit more complicated, but it's the same story. So let's try to do OR swap. I think that's a good one as well. So I'm going to cheat. I'm going to keep at least you know, the basic frame. You know, this is something we can do mechanically without, you know, really without thinking. You know, transform a goal into some fixes, assumes, and then shows based on the for alls and the implications in the goal. And then we're like, okay, can we do any intermediate steps here? We have A or B. It turns out we cannot, right? Because if we have A or B, we don't know if we have A or if we have B yet. So we cannot extract any information here. So the trick instead is, yeah, it's delayed gratification. It's a bit like what we did also with tactics. We also proceeded in different order than for the end at the tactical level. Even though it was backwards, it was you know, also different. So we start by saying, okay, we're going to prove B or A, right? So we're going to attack this one first, and we're going to wait with that one because that one we cannot exploit now. And if we want to prove B or A, then we're going to do a case distinction on HAB. And if we have an A, then we're going to you know, use it to prove this A. And if we have a B, then we're going to use it to prove this B. So the case distinction for an OR, that's elimination. We're talking again about taking this here and, you know, tearing it apart, right? But now in a context where we're going to be able to use the result, which would not have been the case here. So okay, that's OR elim HAB. And then if I just I remove this underscore, then I think it's not very happy because you know, there are not enough arguments. So if we look at elim, this one is a bit difficult, right? So that's why I wanted to do it live. It takes 1, 2, 3 arguments, right? And we've just passed 1. So we're going to add 2 underscores here. And then it's much happier. And sometimes we don't know and we don't want to use checks, so we just start, you know, adding underscores until it's happy. That is perfectly normal. You don't have to be ashamed of doing that. That's what the pros do as well. Sometimes we have like 20 underscores, it's crazy. Okay, and now we see by hovering over these underscores what goals we have to prove, and then we can recursively, you know, use assume, use show, and so on. So I'm going to do the left branch here. I can predict this will get big, so I'm going to put these on their lines. All right. Right. So here the goal is A implies B or A. What is the top level symbols and implications? So I'm going to do an assume. I'm going to say assume A, show B or A. And very important, I need parentheses at this point, otherwise this is not going to work. assume, well, I give it a name, HAA. There are many syntactic traps in Lean, so have to be careful. You just say assume A, then that doesn't mean same as assume HAA. We say show B or A from underscore, right? You have to be very disciplined. Well, it is formal logic. This is a formal logic course. This is all about discipline. If you don't like discipline, then you don't like logic. Yeah, you should take a different course. I'm not going to tell you which one, but yeah. Okay, so okay, we've made some progress. Now, okay, we have the same goal here, but now, well, not the same. We have B or A, right? That's the goal, and we have A in our context. How can we do that? Well, we're almost there, right? We just need the introduction rule for OR that goes into the right-hand side, you know? Because to prove B or A, you have two ways of doing it. You can do it by providing B, a proof of B, or by providing a proof of A. So that means there are two introduction rules, and we'll take the second one. So OR intro right HA. And it doesn't work, and I'm guessing it's yeah, it's just because of the way. I mean, this is where check helps. It has this annoying for all A here, so you have to provide the A, right? So it doesn't only require you to provide a proof of B. Sorry, well, depends on what to talk about, but doesn't only require us to provide a proof of A, so HA. It also requires us to provide B itself, not a proof of B, but it wants to know, you know what is going to be on the left-hand side of the OR. So it just wants to know this, and we can provide it explicitly, and then it's happy, or we can put an underscore, and it can actually infer it itself in this case, so it doesn't matter. And then the other case is going to be very analogous. I'm just going to copy paste and try to guess what's coming. Like this, I guess. And we're done with the OR swap, right? So this is the more difficult one. I mean, because you have the OR elim here, which is a quite nasty elimination rule, and you have all these nested proofs. So if you master that one, then I think you'll be in pretty good shape, because the course will not put too much emphasis on structured proofs. We'll use mostly tactics, or in fact, you can use whatever you want, but in the official answers, we're going to use tactics from now on. So apart from those exercises, you know, this week, I mean, exercises that say we want a structured proof or we want a tactical proof, then of course you have to provide the style we asked. But you know, from lecture 4, we're not going to tell you what to do, and most students tend to use a tactical style for almost everything, because we don't do big proofs that are so big that you need structure. Or you can always structure a proof by adding lemmas as well, so that's another way. Okay. Still, the structured proofs are useful, you know, on a small scale. So even if you like tactics, you're going to find that, you know, once in a while it's useful to do these kinds of, you know, one-liners, proof terms. So that's always a good thing to know. Here's another example with an exist. An exist is a bit like OR, right? So it also spits out has an extra argument where the proof goes on, right? So you have to prove that double 0 equals 0. And this is done, you know, in a very trivial way here, right? So here I'm showing, you know, fairly pure proofs, well, you know, that are as structured as possible. But if I don't mind mixing tactics and structured proofs, I could just write by REFL. And this is what the following example does, actually. Okay. HP, I'm sorry. I mean, this is just another example. It's not very difficult. Another one. I like to show many examples. You can study them at home, but I'm not going to go through all of them now. Then there's something called a one-point rule. So this is a concept. This is just an example, but it's a useful example, something useful to know about logic. So one-point rule is when you have a quantifier that ranges over only one value. then the one-point rule allows you to eliminate that quantifier and simplify the formula. So here you say for all x that are equal to t, you have p of x. Well, there's only one x that's equal to t, right? So you might just as well write p of t. So this is silly. It's silly, but these things do happen. They do arise in practice for various reasons. Usually you instantiate a framework, and then one of the conditions that falls off has this shape, for example, right? Humans don't write these things, but they can still emerge when you do theorem proving. And here's a very long, of course, there are much better ways of proving such a formula, much shorter ways. But again, we're still just developing our muscles here. So this is the structured proof version of it. So the first thing we do is an if and only if intro, because the topmost symbol is an if and only if. And then we end up with two cases, right? One implication, left to right, and the implication right to left. And then the proofs are basically how we've learned to do them. So I'm just going to do the second one here. All right. Actually, I'll just walk through it because I don't want to waste too much of your time, right? So, okay, let's look at the goal, right? We see we have this implication here. So P of t implies a big for all. So implies here is the topmost symbol. We have an assume. So, we have an assumption. So we write the assume here, right? And then if I write the underscore to see the rest of the proof, I hope it's going to show it to me. There, no, it doesn't want, because there's this proof here. Well, let's just do it without guidance because it's actually not very, normally you would do it step by step and you have the underscores and you have the information, but here let's just do it using our heads for a change, right? So, so what we're going to want to, right, so first you have this assumption here, then you have the for all, so that's going to be a fix x, and this is what you see upstairs. Then you have the equation, that's the assume HEQ equation. And then you have the show PX, right? So this accounts for these 4 lines. These are fully mechanical, just based on what we saw in the goal. And at this point here, we have to write a tactic, well, or something, a proof, and then I went into tactic mode here. I just couldn't stand it anymore. So I looked at the goal and I said, well, we have P of t as an assumption, we have x equals t, we have P of x. What did we learn in last lecture? That we have nice rewrite tactics like RW. So I'm going to rewrite the goal so it says P of t. And then I have the assumption that's an exact match, right? So I could write assumption as well, that would work. And one reason I don't like assumption so much is we don't see the dependency. We see the HP here, and it looks as if HP is not used. This shows the connection, so it's a bit superior. One might think, oh, maybe you don't need the assumption, but here you see you really need it. And now we see this is a concrete instance of the one-point rule, right? So you have the complicated version here. If n equals 666, then beast is greater than n. If and only if beast is greater than 666. And in fact, the beast is certainly greater or equal than 666 because it is 666, right? Everybody knows that. So what we can do is just, well, this is an instance of the one-point rule. All right, so I could say by apply, or I can, supply the proof as a proof term directly, but with 2 arguments. And here it's smart enough to infer the arguments, right? So the first one is 666, and the second one is the predicate here. Let me see. And we see the predicate. It's a predicate from alpha to bool, and it's basically P of t, right? So it's the P of t. So it's basically this part here, right? But this doesn't compile. We need a lambda. something like that. Then we're fine. And when we print it, then we see our lambda here. And if we put an underscore instead or another underscore here, then we see the exact same thing. So lean is a unification procedure. You know, it's kind of matching procedure, matching the lemma against its use. It's strong enough here to, I mean, to compute the right predicate and see that this is a fit. And this is an exercise for home where we have the exist one-point rule. So there's also a one-point rule for exist, but you see it's not with an implication, it's with an and instead. So it's a bit different. And again, you have two directions because it's an if and only if. You have the easy direction and the hard direction, like almost always the case with an if and only if. And you see the congruence closure is used at the end to get rid of some you know, basic goals. So here, you see you have something npx, and then let's see. Oh, we have this exists here. So I'm not too sure, but I'm not too sure which. I think it's this one here, to which you know, congruence closure is smart enough to infer that that means that p of t. So at that point, I was like, okay, let's just stop. This is too easy. I wonder, maybe the whole thing goes through by the congruence closure. No, it's not that powerful. Okay, I was just wondering for a moment. Okay,